So reactions involving gases. We learned how to do mass stoichiometry and solution stoichiometry. When we've got a gas that's the reactant or product, we're usually going to specify its amount as a volume at a certain temperature and pressure. So we can use the ideal gas law to find out how many moles there are from pressure, volume, and temperature information, and then we can take the moles in the mole-to-mole part in the middle. When the gas is at STP, things become easier because we can use 1 mole equals 22.4 liters. Remember, you can only use that for gases, and you can only use it at STP. The pressures in these problems could be partial pressures because a lot of times there's going to be mixtures. Here's our general conceptual plan for stoichiometry: mass, grams to moles to moles to grams. And so here's a new variation that we could put on both ends or just one end. We can have pressure, volume, and temperature of a gas because that allows us to calculate the moles. And then we can go moles of the other thing. And if that's a gas, we can also come up with pressure, volume, temperature of that gas product. So in the following reaction, 4.58 liters of oxygen was formed at pressure equals 745 millimeters of mercury and temperature equals 308 Kelvin. How many grams of Ag2O decomposed? Well, I'm told that there's 4.58 liters of oxygen. So here's the oxygen, 4.58 liters. And so that's its volume. And I'm told that the pressure is 745 millimeters of mercury, and the temperature is 308 Kelvin. And the question is, how many grams of this? So we've got a chemical reaction, we've got information about reactants and or products. This is stoichiometry. So we can start with grams to moles to moles to grams. And it is asking how many grams of this. So grams at the end is just fine. But at the beginning, we don't have the mass of oxygen. Now, could we calculate the mass of oxygen? We could, but we don't need to because we can use the ideal gas law to take this information and directly calculate the moles of the gas. So instead of having a mass here, we've got pressure, volume, and temperature, and that allows us to calculate moles of gas. We do need N. N is the number of moles. Well, we are going to solve for it. This is N. That's okay. Ag2O. Yeah, so we don't need to use the molar mass of oxygen. So I've got my pressure in millimeters of mercury, and it's got to be in atmospheres. So I have to convert that. .98026 atmospheres. So I need to get the number of moles of oxygen. So I'm going to use the ideal gas law. N equals PV over RT. So the pressure, I converted it on the side. I also want to show you kind of a shortcut for those of you that are good with your calculators. Here I can put 745 divided by 760 atmospheres as the pressure, and I can do the math inside my overall equation. So if that makes sense to you, that's great. If it doesn't, I'm going to do it the other way. I did the conversion, 0.98026 atmospheres. The volume is already in liters, so that was nice. Down here I've got R. And temperature is 308 Kelvin. So this is equal to 0.17763 moles, and that's moles of what? Oxygen. So I'm right here. This is N, and now I'm going to go from moles of oxygen to moles of Ag2O and then grams of Ag2O. So those units cancel out. And those units cancel out. The mole ratio comes from the balanced chemical equation. 2 moles of the silver oxide for 1 mole of oxygen. And then down here, I need the molar mass of Ag2O. It's 2 times 107.9 plus 16. $231.8. So 0.17763 times 2 times 231.8 equals 82.349 grams, 82.3 grams of silver oxide must have decomposed to form that much oxygen under those conditions. Any questions? $82.3 grams. So here's one at STP. So here we have at STP. How many liters of oxygen at STP are required to form 10.5 grams of water? So water, 10.5 grams. And the water is a gas there, but we're given the mass, and so we can just use that. At STP tells me I can use what? The 22.4. 22.4 liters of a gas is equal to 1 mole at STP. So the question I have posed to me is how many liters of oxygen? So question mark, liters. So normally we would say grams to moles to grams. And here I am starting with grams, but I'm trying to get to liters. So I'm switching up the end this time. From moles to liters, I can use this relationship because it's at STP. So that makes this one pretty easy once you see what you're doing. 10.5 grams of water, grams of water to moles of water, 2 moles of oxygen, to liters of oxygen. Moles of oxygen down here. Those cancel. Moles of H2O. And grams of H2O. This is variations on a theme. I happen to remember the molar mass of water, and we don't have a lot of time, and so I'm just going to tell you. The mole ratio, 1 mole of oxygen, 2 moles of water. 1 mole of oxygen, 2 moles of water. Here, it's 1 mole is 22.4 liters. 1 mole is 22.4 liters. You can only use that at STP and only for gases. Could you use the ideal gas law and calculate that? Sure you could. STP tells me what the temperature and the pressure are, and so I could calculate it. It would take a little longer, but I could get the same answer. So 6.53 liters of oxygen. Any questions? $6.53 liters.